Okay, this problem involves a suggestion system, which we're going to analyze using a paired t-test. But naturally, we'll start with a cartoon. Now for the problem. What we have here is a random sample of 6 employees, and we have after and before scores, which are job satisfaction levels measured on a 10-point scale. And what we want to know is, can we be confident that the suggestion system leads to higher job satisfaction? We use a paired t-test because we have one population, so we have a sample drawn from that population. For example, we have an after and a before score. First thing we'll do then is compute the differences. So for Morgan, we have 8 minus 6 is 2. For Mel, 6 minus 8 is minus 2, and so on. Now once we've done this, that 2, minus 2, 4, 3, 1, and 4 becomes the random variable for this problem, the difference or the improvement. Next, we'll compute the sample mean, sample standard deviation, and standard error based on those differences. So here's the data and our data table. Our sample mean is going to be the sum of the x's divided by n, or 12 divided by 6, which is 2. Then we get our deviations and our deviations squared, and we'll calculate the sample standard deviation. The sum of the squared deviations divided by n minus 1, that's 26 divided by 5 is 2.28. Then we'll get the standard error by dividing that standard deviation of 2.28 by the square root of the sample size, which is 6. We'll end up with 0.931. So we're going to write our null and research hypotheses. Our research question, if you recall, is, can we be confident that the suggestion system leads to higher job satisfaction? So our hypothesis is that the population mean is greater than 0. Our null hypothesis then is that the population mean is less than or equal to 0, or of course we could put mu equal to 0 for that null hypothesis. Okay, we have a one-tailed test. We want to know if mu is greater than 0. Alpha is equal to 0.05, that was given. And our degrees of freedom is equal to 6 minus 1, that's n minus 1, and that's 5. So using the t-table to get a critical value of 2.015, we're going to reject HO. T-test is greater than 2.015. Remember, we had a one-tailed upper test. So to calculate the t-test itself, we'll take the statistic minus the hypothesized parameter over the standard error. In this case, that's x bar minus mu h divided by the standard error, or sx bar. So now we're going to reject HO, because 2.15 is greater than 2.015, and we can be confident that the population mean improvement is greater than 0, and that the difference between the sample mean and the null hypothesis is unlikely to be due to random error alone. Now we'll look at the p-value approach. We have our sampling distribution here, distribution of the sample mean, hypothesized population mean of 0, and a standard error of 0.931. So our sample mean was 2. We calculated the t-test to be 2.15. Then using a TI-83, we can determine that the p-value is 0.042. So if the population mean improvement is 0, then there's a 0.042 or 4.2% chance of obtaining a sample mean difference of 2 or greater. So since that's a small chance, less than 0.05, we're rejecting HO. Now we'll calculate the 90% confidence interval, the sample statistic plus or minus the confidence coefficient times standard error, 2 plus or minus the 2.015 times 0.931. So we're going from 0.12 to 3.88. That interval does not include 0, so again, just like with the hypothesis test, we can conclude that the population mean improvement is greater than 0. Now we turn to the issue of sample size. We want to know if it's large enough, and if not, what assumptions we need to make in order to have valid statistical inference. Okay, our sample size is less than 15, it was 6. So now we have to assume or have some knowledge that the population from which the sample was drawn is at least close to a bell shape. Look at the problem characteristics. Element was an individual employee. The variable was the improvement in job satisfaction rating. And possible values could be 2, -1, 4. The population was all employees with a parameter of the population mean mu, and a sample, 6 randomly selected employees, and the statistic then is the sample mean, or X bar. Now I want to present just a model of the problem that we just covered. So what we're suggesting is that suggestion system causes job satisfaction. I want to also note here that it is measured, that job satisfaction is measured on some kind of rating scale, probably as part of a monthly survey. So now what I want to do is get into the habit of thinking critically about the problem. Now that suggestion system wasn't implemented in a vacuum. Other things are going on. We don't have experimental control. So that means we need to look at plausible or alternative plausible explanations for why job satisfaction may have improved. Well, maybe the supervisors were nicer during that time period, perhaps because they knew the suggestion system was being tested. Maybe there was some kind of pay raise during this time period, maybe one that was larger than usual. Well, maybe the company hasn't paid a lot of attention to employees in the past, and just the attention itself, having a suggestion system, may affect job satisfaction levels for employees. Some of you may know that as the Hawthorne effect, something you either have or will study if you take an introductory management class. Also want to look at how reliable and valid that rating scale was. You need to look at measurement. Not all surveys are going to give you an exact measure of what job satisfaction is. I also want to know if anybody is going to stand to gain from that suggestion system being implemented. Maybe whoever came up with the plan is expecting some kind of reward for getting his or her plan implemented. Well, even with those questions, we do have statistical evidence that supports the idea that job satisfaction did improve. We had a sample mean improvement of 2 on a 10-point scale. That seems like it's pretty significant, even just from a practical perspective. Not only that, implementing a suggestion system probably won't be very costly, and it may have other benefits. Not all of them. Some ideas might even be good. Might lead to process improvements, improved product quality, cost savings, and so on.